All right, let's dive into one of Go's absolute killer features. It's super simple, but incredibly powerful toolkit for concurrency. We're going to see how Go manages to juggle literally thousands of tasks at once and somehow not even break a sweat.
I mean, really think about that for a second. You've got a web server getting hammered with user requests, or maybe a data pipeline just chugging through massive amounts of information. How does all that chaos not just bring the whole system to its knees? How do they stay fast and responsive?
Well, it turns out Go has this really elegant answer to that exact problem. And today, we're going to break it all down. We're going to look at each piece of the puzzle one by one, see the problem it solves, and then put them all together to build something awesome.
Okay, first things first. Before we go any further, we have to get one thing crystal clear because it trips a lot of people up. There's a huge difference between dealing with a lot of things and actually doing a lot of things.
And this slide just nails the difference. Concurrency is all about structure. It's about managing a bunch of tasks by intelligently switching between them. So the jogger is handling both running and tying their shoe, but not in the very same nanosecond. Parallelism, that's about execution. It's doing multiple things at the exact same time, which means you need multiple CPU cores. Go is built for concurrency, which makes it incredibly good at enabling parallelism.
So how does Go actually pull this off? Well, the first and most fundamental building block is something called a Go routine. You can think of a Go routine as just a function that's running off in the background. But here's the magic part. They are so cheap. A normal operating system thread can be pretty heavy, but a Go routine, it starts with just a tiny bit of memory. This means you can have thousands, even millions of them running at the same time without crushing your system. The Go runtime takes care of all the messy details of scheduling them for you. And this is the best part. Starting one of these concurrent tasks is this easy. You literally just put the word Go in front of a function call. That's it. The main program just keeps on trucking, and that new task starts running in the background. It's just beautifully simple. But that incredible simplicity, it creates our very first problem. That Go keyword is kind of like fire and forget. Your main program doesn't wait around. And here's the rule you gotta remember. When your main program ends, the whole show is over. All the other Go routines get shut down immediately, whether they're finished or not. So, how do we make the main program wait? Now, we could do some hacky stuff like telling the program to just sleep for a second and hope for the best, but Go gives us a much better way. And this brings us to our second core building block, channels. Think of a channel as a pipe connecting your Go routines. You can push data into one end, and another Go routine can pull it out from the other. But here is the absolute key, the most important part. By default, sending and receiving on a channel are blocking. If you try to send something, your Go routine will literally pause until another one is ready to receive it. That blocking is the secret sauce for synchronization. This shows you exactly what I mean. On the left, you've got the fragile, unreliable hack. Just guessing. But on the right, that's the Go way. The main program just waits to receive a signal from that done channel. It's not guessing. It waits for exactly as long as it needs to. The background Go routine does its thing, sends a little true signal down the pipe, and that unblocks the main program. It's communication and synchronization, all in one. So clean. All right, so we've got the basics down. Go routines and channels are our bread and butter. But, as our programs get more complicated, we can start to create new kinds of, traffic jams. So what happens if you have one Go routine that's producing stuff way faster than another one can consume it? With a normal channel, that super fast producer would just be stuck all the time, blocked, waiting for the slow consumer to catch up. And that tight connection, it can grind everything to a halt. And the solution is a buffered channel. Think of it like giving that pipe a little waiting area, or a queue. When you create it, you give it a size. Now the sender can drop a few items into the buffer and just move on, without waiting. This separates the sender and the receiver, letting them work at their own pace. It can make a huge difference for performance. Okay, now for a classic, and I mean a really dangerous problem in the world of concurrency. Let's imagine you have a shared counter, and a bunch of Go routines are all trying to add one to it at the same time. The code looks simple enough. X equals X plus 1. What could possibly go wrong? Well, this situation creates something called a race condition. See, X equals X plus 1 isn't one atomic step. It's actually 3. First, read the value of X. Second, add 1 to it. Third, write that new value back. Now, if one Go routine reads X when it's 5, but gets paused before it can write back 6, another Go routine can swoop in, also read 5, and then they both end up writing 6. An entire increment just vanished into thin air. Your final result becomes totally unpredictable. The classic way to solve a race condition is with a mutex, which is short for mutual exclusion. It's basically a lock. Before a Go routine touches that shared data, it has to acquire the lock. When it's done, it releases it. If another Go routine comes along and tries to get the lock while it's in use, it just has to wait its turn. This guarantees that this critical section of code is only ever run by one Go routine at a time. Problem solved.
So, this is the big question. When do you use a channel and when do you use a mutex? The rule of thumb in Go is pretty clear. You use channels when you need to communicate between goroutines, when you're passing ownership of data from one to the other. And you use mutexes when you just need to protect a piece of shared memory, making sure only one goroutine can mess with it at a time. Okay, we have our building blocks. Goroutines for doing things, channels for talking, and mutexes for protecting. Now, let's put it all together and build one of the most powerful and common patterns in all of Go.
I'm talking about the worker pool. The whole idea is simple. You create a bunch of Go routines, your workers, and they all just sit there ready and waiting for work to come in. This pattern is amazing for things like processing jobs from a queue, handling a ton of web requests, or anything you can break into smaller parallel tasks.
So here's how it's built. You have one Go routine, the producer, that creates tasks and drops them onto a jobs channel. Then you have your pool of workers, all pulling tasks from that same channel. They do the work, and then they send the results onto a different results channel. And finally, we use one last little tool, a wait group, which is just a simple way to make sure our main program doesn't exit until all the workers are completely done. It's a beautiful machine built from all the parts we've just learned.
And here it is, the payoff. With this worker pool pattern, making your program faster is as easy as changing one number. In this example, just by doubling our workers from 10 to 20, we literally cut the total processing time in half. This is how you get those incredible performance gains by using all the CPU cores you have available. So there you have it. We went from the simplest building blocks, Go routines and channels, all the way to a powerful, scalable pattern. Go gives you these amazing tools to build ridiculously efficient systems without all the complexity you might expect. So the only real question left is, what are you going to build with them?